Alright, our next section is called 15.2. We're here in lesson 15, of Unit 4. And yeah, I want to retire a millionaire, so this one definitely has my attention. I would absolutely love to retire a millionaire. Let's see how we can get there. The expression 1 times e raised to the 0.06t models the balance in thousands of dollars of an account t years after the account was opened. So I'm taking notice that we're getting an output of thousands of dollars. Okay. I know I'm going to be using some Desmos on this lesson, so if you want to take a moment to get a Desmos screen ready, we will be looking at that in just a couple minutes to see how we could graph this to solve it. But it asked me first to do some interpretation. What is the account balance when we first opened it? And we have started from the very beginning of this unit, still thinking of box times box to the box, right? Always thinking about our starting value, how it's growing, and how much time we have given it to grow. That has been our general format for all of our equations. So when I look about this, about how much is in the account when it was opened, there's our starting value right there. But it's not just $1. Remember, this is in thousands of dollars. So because it's in thousands of dollars, the account was opened with $1,000 to begin with. After 1 year of time, I would just be able to plug 1 in for that exponent. So I'd have 1 times e to the 0.06 times 1, but we know that's just the same as 0.06 because 1 doesn't change its value when we multiply it. So I'm really just looking at taking e raised up to the 0.06 exponent. So I'm going to grab my cell phone calculator. Grab your graphing calculator if you like. You can certainly use it all these different ways. Actually, it's been a little bit since I used my graphing calculator. I'll do that side by side. And so I want e raised to the 0.06. The e on your graphing calculator is at the second divide button. So second divide brings up e. I'm going to use the caret to raise it to the 0.06 power. And I find 1.0618365547. If you're using yours here, you would use that e to the x button. And we want to bring e up to the exponent of 0.06, e to that exponent. And we've got the same value in either place. So remember, here on your calculator, you do have to do the input first and then say, hey, I want to use that x as an exponent. So after 1 year, we would have $1,062 if I was rounding to the nearest dollar. Again, it's in thousands of dollars, so I know I have just a little over $1,000 here. 1,062. And after 2 years, I would have e raised to the 0.06 times 2. 0.06 times 2 is 0.12. And it's already in my calculator here, so I'm just going to hit the e to the x button so I can see that that's e raised to the 0.12 power. I would have $1,127 and about 50 cents in this account. So now it's asking if Diego says that the expression ln5 represents the time in years when the account will have $5,000. Do we agree, and we should explain our reasoning? Here, what we're seeing in the account is the unknown exponent going on. So it's thinking like, well, this is putting in a 5 there. But what we've said many, many times throughout this unit is that the natural log, or the log, the whole purpose of it is to isolate the exponent. Whatever this ln of 5 equals, that would be the exponent, not this $5,000. Well, I don't know. Let's see. Let's rewrite this in a different way. If we have ln 5, to rewrite it in this format that we have, exponential form, or we could even take this and write it in logarithmic form, which might be a little easier. This is telling me that I'm going to roll that base e to the other side, and we would have 5 equals base e to some unknown exponent. So that does make sense. The expression models the balance that we would have of an account after a certain number of years. Now, it wouldn't exactly tell us that how many years we'd still have to use this 0.06t, but this is telling me that if the output of this e raised to the 0.06t, if the output is the balance of the account in thousands of dollars, yeah, this would be how long it's going to take for us to get to $5,000 in the account. Looking at it the other way, if I took our existing account, what we have here, this 1e to the 0.06t equals the balance well, when I roll that e to the other side, remember that's natural log of e, so ln of the balance would equal 0.06t, how much time it takes me to get there. So yeah, ln5 would be the balance of $5,000. So 2 ways we could look at that with the input and the output. So I'm going to say yes, we would agree. So suppose we open this account at the beginning of this year and assume that we deposit no additional money and withdraw nothing from the account. It's just going to sit there and grow. Will the account balance reach $1 million and make you a millionaire by the time you reach retirement? We need to know a couple things. We need to know when this function is going to reach a value of 1,000. Now notice I'm putting in 1,000 because remember our account is already in thousands of dollars. So it's already in thousands of dollars, so if we put in 5, it would be 5,000. We put in 1 at our beginning, we had 1,000 to begin with. So we would just need it to equal 1,000. Watch that units that we have. So we can solve this and figure out how many years it's going to take for us to be a millionaire. And then you'll have to do something kind of on your own about how much time before you reach retirement. If we assume that we retire at age 65, you could take your age right now, subtract it from 65, and see how long you would have to be letting this grow. Now you guys would have much longer than I would. Right now I'm 42. So if I take 65 and I subtract 42, I only have 23 years for this to grow. You guys have much more. You guys probably have close to about 40 years for this account to grow. So we could plug in 40 and see what the output would be. But I like the idea of this. How long is it going to take it to grow to $1 million? Now I mentioned I'm going to use my Desmos to solve this, but I also want you to know that we could roll that e to the other side. We saw in our last lesson how we can solve any equation just using straight up algebra. So the amount of time we would need is the natural log of 1,000 divided by 0.06. On my calculator, the natural log of 1,000 and then divided by 0.06 is going to tell me that I need about 115 years for this to become $1 million. Now, even if you guys are younger than me and you have 40 years to get there, it's not going to make it to $1 million by that time. So it would take 115 years for this to grow. Again, we could also tuck this in on a Desmos, plugging in our equation, our e raised to the 0.06x, and see how long it's going to take to get to $1 million. Remember, represented by 1,000. I need to zoom way out because I need to see way up at 1,000. Oh, and I always forget that. I need a horizontal line, so I need it to equal 1,000. I need a y equals 1,000. And I would see right there we're getting that same idea, that it would take us 115 years, over 115 years, to reach that amount. So, not going to happen. Sorry, friends. Got to invest more than $1,000 right now and let it sit there at this interest rate of 6% growth interest rate for it to become $1 million.